So welcome to our second lecture on functions. So today we're going to define functions and talk about injective, surjective and bijective functions. So let me first give you the definition. So here a function is usually denoted as the following, where we have a domain x here of the function f and a codomain y of the function f, and it's a way of assigning to each element here in x exactly one, and so this is important, element in y. And then we write f of x for the unique y assigned to x. This here is often also called the image of x. Okay, let's go on with some notation. So what we do here is we write f x to y, comma x maps to f of x. Okay, and so first let me give you some examples. You probably already know a lot of functions, and functions that you definitely, I would say, most familiar with are just functions from, let's say, R to R. And one example could be here, well, let's say we assign x to x squared. But really this f can go from any type of set. So let's say we have the set A, B, C, and we map this to the set, let's say 2, 4, 8, 16. And so now this is finite, so I can really just tell you where every element goes. Let's say A goes to 8, let's say B also goes to 8, and let's say C also goes to, let's say 2. Okay, and here you see that it's not necessary that every element in the codomain here gets, let's say, hit by an element from the domain. And so then there's 3 important properties of functions that we want to study. So the first one is being injective, or what we also call one-to-one. And it really means that every element gets sent to a different element. So if we have that the images of 2 elements coincide, that can only happen if the elements were already the same. So above here, if we go back to the functions here, we can ask ourselves, is the first function injective? Well, here we have that 1 gets sent to 1 and minus 1 gets sent to 1, so it's not injective. Okay, so this is the first property. Let's go to the second one, being surjective. And so this means that that every element in the codomain gets hit. Yeah? So sometimes we also call this onto. And so what does it say is that if I take an element in the codomain, then I can find an element in the domain such that the element gets mapped to y. And so now let's go here. If I look at the first one, well, this is also not surjective because I only have positive real numbers in the image. And let's go to the second one. What do we have here? Well, again, this is not injective because A and B get sent to the same, and it's also not surjective because nothing gets sent to 4 and nothing gets sent to 16. And the last property is the ones combined, so we call a function bijective if it's injective and surjective at the same time. And then we also have nouns for this. So we call a function that is injective, injection, we call a surjective map surjection and a bijective map bijection. And before I go on, let me give you some more examples. And what I'm going to kind of focus on here is the map that we already looked at, f of x equals to x squared. So we saw first, and this was the one before, if we let it just go from r to r, sending x to x squared, this is not injective and not surjective. But what I kind of want to show you here that these two properties highly depend on what do you choose to be your domain and your codomain. So let's look at the second function, and we want to really give the same assignment. So we want to send x to x squared. But instead of the domain being r, let's say it's only the positive real numbers. So I don't know if you're familiar with this. So this set here, x plus is defined as all, let's say r and r, such that r is greater or equal to 0. And so now what do I have here? Well, this is actually now injective, yeah, because two positive real numbers get sent to two different squares. But it's still not surjective. Yeah, because none of the negative numbers here get hit. But then I can do a similar trick of, instead of restricting the domain, I can restrict the codomain. And what I'm going to be doing here is actually I'm going to do both. So let's look at the interval -1, 1, and let's assume the codomain is what, 0, 1. And again, I'm going to just let x be assigned to x squared. So now what happens? Well, again, -1 and 1 gets into 1. So this is again, as the first one, not injective. But now we restricted the codomain small enough such that every element has a preimage. So this is surjective. And then last, let's create a function that is both. Let's say f4. And here let's just restrict to both the positive real numbers. And so now this is injective and surjective, so this is bijective. Great. So now I've just given you examples, but in this class we want to be able to prove that certain functions are injective, surjective. So let us have another proof strategy. And so now we want to learn how to prove that a function is injective. Okay, so I have the next box here. So let's go through the bullet points. And then the first line is pretty much similar to our guidelines from before. We always let the reader know what we want to do. So first, we say we wish to show that a function f is injective. So let f from x to y be a function. Then we tell what was going on here. Then by definition here, we have to show that whenever f coincides on x1 and x2, sorry, this is a typo here, this should be x2, then x1 and x2 already have to coincide. So now suppose that f of x1 is equal to f of x2, and then we come to the third bullet point where we have to tailor to our specific situation we're in, and then again we have our ending, our conclusion. So you can see there's very much similarities between different proof strategies. It's really just always the setup in the beginning where we tell what's going on. Then the middle part really depends strongly on the situation, but then the ending, again, it's like always the same. We want to conclude that whatever we've shown is correct. So let us do this once. Proposition 2.3 in the lecture notes. The function f from R to R, where I map x to 2x minus 1, is injective. Now the proof. And so we go along the line. So we wish to show that f from R to R sending x to 2x minus 1 is injective. By definition, we must show that if f of x1 equal to f of x2 for x1, x2 in R, then x1 is actually already equal to x2. So here, note that whatever you write here has to be the domain. Okay, so then suppose that f of x1 is equal to f of x2 for x1, x2 in R. Again, here comes the domain. So these are this is the setup again, introduction, and now we go to the specific situation we're in. So let us analyze what f is really doing. So by definition of f of x1 being equal to f of x2 yields that, well, what is f of x1? Go back up to here. It's 2x1 minus 1. And what is f of x2? Well, we go back to the same assignment, so this should be 2x2 minus 1. Okay, and then this now is equivalent to, well, if we add plus 1 on both sides, then we get here 2x1 equals to 2x2, and then if we divide by 2 or multiply by 1/2, we get x1 is equal to x2. And so this is the argument, and then we come to our conclusion. So we conclude that x1 is equal to x2, and so we have shown that f is injective. Then end of the proof, my box, which doesn't look great right now. Okay, so this should be a box. Great. So again, you can compare, maybe go back and forth a little bit between the two, but you can see that then pretty much these parts over here, again, are copy. And then this is somewhat what you have to come up with yourself, and then this one is again copy from before. Okie dokie. So this is how we show something is injective, and so the next step would be, how do we show that something is surjective? So this again is a proof strategy here. And so then let's start. So first line, always we tell the reader what we want to show. So we wish to show that f is surjective. Then we write down what does this mean. So by definition, we must show that if we pick something in the codomain y, we can find something in the domain x such that f of x is actually maps to y. And so now let's take such an element in the codomain. And so the next step is we really want to show that we can find such an x. And the best way to do is to actually really find it. So what we do here is usually we want to specify an element x and x, and then we check that this specific element satisfies the equation. And so here often actually the way you present the proof in the end is not really the way you come up with it. Obviously, like, it's very difficult to just guess what this x should be. So first, right, you have to kind of figure out, go from the bottom up, take your y, try to figure out what x is. But then if once you present the proof, you really want to start with, like, given the x at the beginning and then show that this is true. This is just the easiest way of presenting it. It might be a little misleading in terms of following what should be the ideas of how to come up with the proof, and it might be difficult for you to cope with the thing, like not cope, but to understand where all this is coming from. But it's usually because the presentation of the proof doesn't necessarily follow the way you come up with it. Okay, and then the ending, as usual, we just conclude, yeah? This is then the conclusion. But maybe this middle part of how to specify the x becomes more understandable once we do the example, and we want to stick here with the same function as before. So proposition 2.4 in the lecture notes. So the function f r to r, where I set an element x to 2x minus 1, is also surjective. So we start our proof. We wish to show that f is surjective. By definition, we must show that for any y and y, there is x and x such that f of x is equal to y. So suppose now that y is in y. And so now let x be defined as y plus 1 divided by 2. And see, like, maybe this becomes, kind of looks like it dropped from the sky, but this is what I was talking about before, that I, on the side, figured out which x it should be, and then now I'm really going to start with this x. And you'll see that this is probably the easiest way to really present, because now I can just apply f to this. So then f of x is equal to f of y plus 1 divided by 2, but this is then going to be 2 times y plus 1 divided by 2 minus 1 by definition of f up here. Yeah? And now if you simplify this, this just really becomes y. And so now we can conclude that f is surjective. Okay, so then now we have seen how to show something is injective. We have seen how to show that something is surjective. Now the last one is how do we show that something is bijective? Show that f from x to y is bijective. And so this somewhat should remind you a little bit of the proof strategy, showing that two things are equal. Remember, two sets are equal if one is a subset of the other. And so in the proof strategy, we had these 2 bullet points where we referred to the older proof strategies. And the same is here, because being bijective means it's injective and surjective. So basically what the proof does is just insert a proof of being injective and you insert a proof of being surjective, and then you put those two together. And obviously, again, you have a beginning and an ending. So let us put this into action as well. And so here you're going to learn another thing you can do in a proof. So first thing, we're going to just stick with the same function. Yeah. So the function from above, so meaning x gets mapped to 2x minus 1, is indeed bijective. So now let's start our proof. So we go along the bullet points. We wish to show that f is bijective. By definition, we must show that f is injective and surjective. So now I have to turn the page, but what are the next 2 steps is to insert a proof that f is injective and to insert a proof that f is surjective, and then conclude. And what we're going to do here now is, well, we're going to refer to things we already shown. So this is something you can do in a proof. You can always refer to results that you have already shown in the class before or on homework or something like that. So what we're going to do here is we're going to say by proposition. And so the number was 2.3. This is where we showed that f is injective. F is injective. And by proposition 2.4, f is surjective. And so, so we have demonstrated that f is bijective. And so this is something you really want to do as often as possible. Kind of, I would say this is kind of shortcutting the proof, yeah? You rely on things you already shown before, so you don't really have to insert the proof anymore. You can just use those results as arguments in your proof. And so now we're getting to the end of this lecture. So first, before I let you go, I have to give you another definition. And this is the definition of a composition of two functions. So now suppose x, y, and z are sets, and that we have one function f that goes from x to y, and then we have another function g that goes from y to z. And so these are functions. Then the composition, so this is what I wanted to find here, of f and g is the function denoted by g f like this. Now what do we really want to do? So the way you want to think about it is like, first you apply f to the function, and then you apply g to the function, yeah? So what you want to do is you want to send a little x to first what, f of x, and then g of x. And so what should the domain be? Well, what can you plug into f here is only things from x. So the domain should be x. And what should be the codomain here? Well, in the end, you're gonna go from x to y. Well, this is where f of x gets you. And then it makes sense to apply g to this because the domain of g is going to be y. And then, well, if you apply it, you're going to end up in z. So what you're going to do is here, this should be a map from x to z in the end. So if you don't know what should the domain or the codomain be, you can always kind of figure it out going backwards. And then another thing is you might find it kind of strange that if you look at here the composition, yeah, it's kind of in the opposite order of what you want to read, yeah? Because we're reading from left to right, so if you write g first and then f, one might think first, well, that means you first apply g and then apply f. But you really want to read this backwards, yeah? So this gets... write it in a different color. You really want to read it this way, yeah? First f and g. And so why do we chose this? It's due to what happens below here. Yeah? Because if you write it like this, then naturally, yeah, you kind of do here first f of x and then g of x. I'm happy to answer more questions about this if this wasn't clear yet. Okay, and so now let's get to our last theorem here. So this is going to talk about what kind of connections you have between a composition being injective and surjective and functions being injective and surjective. So what do we have here? We'll start with sets x, y, z. And functions from x to y called f, and a function from y to z called g. And so we want to show that if f composed with g is injective, then f had to be injective. And if f composed with g is surjective, then the second function g had to be surjective. And that if f and g are injective, both of them, then the composition is injective. And if both are surjective, then the composition is surjective. So let me maybe first say how I would think about these, not really how formally I want to write the proof, but think if you have that the composition is injective, yeah? And now let's look at your little f. Assume it wouldn't be injective, yeah? So... well, then that means f of x1 is equal to f of x2 for x1 different from x2. Now, if you compose this furthermore, yeah, this will never gonna go apart, yeah, because if you now apply g to the same element, then it's gonna obviously send it to the same. So the composition cannot never be injective. and so on, I would recommend you to first think about a little bit, what does this mean, yeah? Why should these morally be true? And then the proofs, 1 plus 4 will be done in the TA session. And then 2 plus 3 are homework. Okay, so that'll be all for the lecture on functions. I hope you could follow, and then I'm happy to answer any of your questions in the Friday lecture.